Greetings, everybody. Learning is a hobby here. I want to continue with Spivak's book. So in this video, I'll be going over my solutions to the selected chapter 10 problems. As I usually do with Spivak, because he has so many problems, I usually pick either problems that are important for things that we'll do later on, or problems that are just, interesting. So let me bring up my solutions and we'll go through them. This was kind of a long exercise set, so this might be a long-ish video, but there's some interesting problems in here. So let me bring up my solutions for you guys to see. All right. The first problem is kind of simple, but important to do because if you saw my video on ch the chapter 10 summary, Spivak gives you the derivative for sine and cosine, but not for the other four trig functions. So here we're going to use the rules that we derived in chapter 10, along with the derivatives for sine and cosine to find the derivatives of the other four trig functions. And this is a relatively straightforward problem. You just have to use some trig identities and the derivative of sine and cosine and the quotient rule to find the derivatives of the other one. So, for example, tangent, if you remember your trigonometry is sine over cosine. So if we want to differentiate that, we just use the quotient rule and we need the derivative for sine and cosine, which we have. And once all the algebra is simplified, you end up with secant squared x. So I'm not going to belabor the steps here. It's very straightforward. Like I said, you just apply the quotient rule and the derivatives that Spivak gave us, as well as you need the Pythagorean identities, reciprocal identities, and quotient identities from trig. All right. The derivative of cotangent is negative cosecant squared. The derivative of secant is tan x secant x, and the derivative of cosecant x is negative cotangent cosecant x. All right. So, like I said, if you want to pause the screen and look at the steps, you can do that. But you should be able to do those on your own. It should be relatively, it's a relatively straightforward application of the quotient rule. Okay, so let's move on then to question 15. If f plus g is differentiable at a and f and g are necessarily are f and g necessarily differentiable at a, if f times g and f are differentiable at a, what conditions on f imply that g is differentiable at a? Right, so let's answer the first question first. So here's a counter example. Let f of x equal x sine 1 over x, x not 0, and 0 if x is 0. And let g of x be negative x sine 1 over x for x not 0, and 0 if x is 0. Then f plus g of x is the function that's identically 0, which has derivative 0 everywhere. So the sum is differentiable for all x and r. However, f and g, notice, are not differentiable at 0. All right, this answer to question number two. We have to derive a condition on an f of a in order to say whether whether g is differentiable at a. So here, fg differentiable at a means fg is continuous at a, which implies that fg of a is f of a, g of a exists, implies g of a is a real number, f of a is a real number, then f differentiable at a implies f prime of a is a real number, then the derivative of f times g at a by the product rule is f prime of a, g of a, minus f of a times g prime of a, and then just solve for g prime of a, and that gives you this expression here. So g prime of a exists provided that f of a is not 0. All right, question 16. Prove that if f is differentiable at a, then the absolute value of f is also differentiable at a, provided that f of a is not 0. So first, I'm just writing out the piecewise definition of the function absolute value f of x. So that's equal, excuse me, that's equal to f of x if f of x is greater than or equal to 0, and negative f of x if f of x is less than or equal to 0. If f of a is greater than 0 and f is differentiable at a, that means that f is continuous at a, which implies that there's a delta greater than 0, such that f of x is greater than 0 for all x in that delta neighborhood. We had a theorem in the chapter on continuity that we proved that said that. All right. Similarly, if f of a is less than zero, then there's a delta greater than zero, such that f of x less than zero for all x in that delta neighborhood. Then, so f of a, let's assume first that f of a is greater than zero. That implies that limit h goes to zero of absolute value f a plus h minus absolute value a over h equals limit h goes to zero f of a plus h minus f of a over h, which is f prime of a. Here I can rewrite this over like this, provided that, a plus h, or provided that h is small enough that we're in that delta neighborhood that I talked about up above. All right, and same thing for f of a less than zero, except the absolute value of f is equal to negative f of x when if f of a is less than zero. Okay, that implies limit h goes to zero, absolute value f a plus h minus absolute value a over h equals limit h goes to zero, negative f of a plus h minus f of a over h. I just factored out the negative from the two terms there. And notice that that's equal to negative f prime of a. So that implies both, case one and case two implies if f of a is not zero, then absolute value f is differentiable at a. And then Spivak asks us to give a counter example if f of a is equal to zero, and f of x equals x is an obvious counter example. That's because we should know by now that absolute value x is not continuous. Sorry, is not differentiable at zero. Right, part C, prove that if f and g are differentiable at a, then the function max fg and min fg are differentiable at a, provided that f of a is not g of a. So here's my proof. Let f of a not equal g of a. Then fg differentiable at a implies fg continuous at a, which implies that f minus g is continuous at a, and f minus g of a is not zero. That implies there's a delta greater than zero with x in that delta neighborhood around a, implies f minus g of x is not zero, right? Similar reasoning that we had up above. Then absolute value f minus g of x is not zero for x in that delta neighborhood. All right, then we'll look at max fg of x first. That's defined. We could write the output using this formula here, which is a formula that we derived way back in, I think it was might have even been chapter one, I forget. It was chapter one or chapter two. But anyway, you can define it like this. By theorem three and part A above, max FG is differentiable at A. All right. And then similar thing for min FG. All right, part D, give a counterexample if f of a equals f of g. So here's my counterexample. Let f of x be 2x and g of x equal x. Then max fg is the defined piecewise like this. It's x if x is less than or equal to 0, and 2x if x is greater than or equal to 0. And clearly max fg is not differentiable at 0. And same thing for min fg. That's equal to x if x is greater than or equal to 0, and 2x if x is less than or equal to 0. Both of those are not differentiable at 0. All right, question 17. Give an example of functions f and g such that g takes on all values and f composed with g and g are differentiable, but f isn't differentiable. And then Spivak says the problem becomes trivial. If we don't require that g takes on all values, g could just be a constant function or a function that only takes on values in some open interval a to b, in which case the behavior of f outside of that interval would be irrelevant. All right, so consider these functions here. F of x equals x sine 1 over cube root x for x not 0, and 0 if x equals 0, and g of x I'll define as x cubed. Then notice that when we take the composition, we get the function that's x cubed sine 1 over x for x not 0, and 0 when x is 0. F composed with g, if you notice, is differentiable, so is g of x, but f is not. All right. Question 19. If f is 3 times differentiable and f prime of x is not 0, then the Schwarzian derivative of f at x is defined to be given by this formula here. Show that the Schwarzian derivative of f composed with g is the Schwarzian derivative of f composed with g times g prime squared plus the Schwarzian derivative of g. So here, I won't read through the whole, a bunch of lines here of differentiation in algebra. You can pause your screen if you want to see it. But first thing I did was I found the derivative of f, the first derivative of f composed with g, then second, and then third derivative, and then I just plugged it into the formula on the right-hand side. uh, which gives, when you work everything out, ends up giving you what you want. So again, you can pause your screen if you want to see when you simplify everything at the end, you end up with the formula. All right. Part B, show that if f of x is ax plus b over cx plus d with ad minus bc not zero. These are sometimes called Mobius transformations, or another word for them is fractional linear transformations. These come up in a bunch of areas of math, like complex analysis and so on. Um, the so here, this is an interesting usage of the Schwarzian derivative. So the Schwarzian derivative of f is zero if f is a fractional linear transformation. Consequently, the derivative of f composed with g is just the Schwarzian derivative of g. So what this is saying is if the Schwarzian derivative of the composition is um, equal to zero, then that means that the composition of two fractional linear transformations is a fractional linear transformation, which is nice. So anyway, here here's the proof. So let f of x equal ax plus b over cx plus d, where ad minus bc is not zero. Then find the first, second, third derivative and plug it into the formula for the Schwarzian derivative, and you'll see that you get zero. Okay, therefore, if f is a Mobius transformation and g is differentiable up to order 3, then if you take the Schwarzian derivative of the composition, then obviously you get the Schwarzian derivative of g. Okay, question 20. Suppose that the nth derivative of a and the nth derivative, I'm sorry, the nth derivative of f at a and the nth derivative of g at a exist. Prove Leibniz's formula so this is sort of like, I guess you can think of this as a product rule for the nth derivative, sorry, for nth derivatives, I guess you could think of it. Um, and so we'll prove this by induction. So induct on n. The base step is just the first derivative of f times g. It's just a product rule, so there's really nothing complicated there. For the inductive step, um, assume that, oh, I just realized actually there's a typo here. Let me fix this real quick. This should be, sorry, just bear with me. These A's should be on the outside of the brackets, not on the inside. And my computer is being slow today for some reason. Okay, so that's true by the inductive hypothesis. And then really the rest is just using the differentiation rules from chapter 10 and just rearranging the sum and get what you want. So we can use the theorem 10.4 and 10.5 from the chapter to get this expression here for the n plus first derivative. And then again, use the product rule for the derivative of this product here. And then I'll just rearrange the sum in a convenient way so that we can simplify everything and we end up with, we end up with the formula that we expect over here. And that proves the Leibniz formula. Okay, question 21. Prove that if the nth derivative of f at g of a and the nth derivative of g of a both exist, then the nth derivative of f composed with g at a exists. And Spivak gives some hints here. He says, a little experimentation should convince you that it is unwise to seek a formula for the nth derivative of f composed with g at a. In order to prove that the nth derivative exists, you will therefore have to devise a reasonable assertion about that derivative. I don't want to keep saying the same thing over and over, which can be proved by induction. Try something like the nth derivative of f composed with g at a exists and is a sum of terms, each of which is a product of terms of the form yada yada, which is what I did here. So I took the first derivatives just to illustrate what the pattern ends up being. And then I made my conjecture and then just proved it by induction. So here's my conjecture. The nth derivative of f composed with g of a consists of sums of products of the form c times f times the kth derivative of f composed with g times the mth derivative of g prime, sorry, not the mth derivative, g prime to the m power times G double prime to the R power, et cetera, where C is a constant and K, M, R, L are between 0 and N. Right, so induct on N. The base step is easy. It's just a chain rule. Let's go to the inductive step then. Assume the conjecture holds for some n in n and consider the n plus first derivative. Then the n plus first derivative is equal to this when you, whoops, is equal to this when you use the inductive hypothesis. Right. And then here, just so I don't have to recopy, all these complicated expressions, I called this, H1 and so on like that, just so it was just easier to write. All right. So when you apply the derivative uh, theorems for that we learned in uh, the chapter itself, you end up with uh, this thing here equaling this, and then again, just applying the general product rule, you end up with this, and that proves that the derivative is a sum of products of the same type. Right? Then the nth derivative of f at g of a and the nth derivative of g of a existing implies all derivatives of lesser order exist. Also, sums and products of differentiable functions are differentiable. Therefore, we get the theorem. Okay, question 22, part A. If f of x is this polynomial here, find a function g such that g prime of f, such that g prime equals f, and find another. I did this in general. If you know how to take antiderivatives, you already know this, but you just used for the polynomial, you just used the power rule, but in reverse, and it's any polynomial that looks like this plus an arbitrary constant. When you differentiate it, you'll get f. And similar thing for part B, except here we have a rational sum of powers, um, which looks like this, and he wants us to do the same thing. But again, you can use the same, the reverse power rule, and you get a function that differentiates to give you f. All right, and then in part C, the reason I chose to do this one is because of part C. Is there a function f of x equal to a sum of a polynomial plus a sum of powers of rational powers of x, such that f prime of x is 1 over x? So the answer is no. If you already know calculus, you know why that is. But I wanted to do that here just to show you that it's if you don't know calculus, then this should be interesting. So there is no function like that differentiates to give you 1 over x. So here, if you differentiate the right-hand side, you assume that there is, and you differentiate the right-hand side over here, then you get an expression that looks like this, and then you multiply through by x to the m plus 1, and that gives you x to the m equals a polynomial that looks like this. And notice that the coefficient of x to the m on the right-hand side is 0, but the coefficient on the left-hand side is 1, and obviously 1 is not 0, so that's a contradiction, which means no such function exists. And again, I will look at this in later chapters in Spivak, but the antiderivative of 1 over x, if you don't know, is actually the logarithm of absolute value of x. All right, but we won't look at that here. All right, question 23. Show that there's a polynomial function f of degree n such that, and then there's a few parts. Part A, f prime of x equals 0 for precisely n minus 1 numbers x. Right, so here let aj, j going from 1 to n minus 1, be n minus 1 distinct real numbers. Then g of x is if you define g of x to be the product of x minus aj, j going from 1 to n minus 1, is a polynomial with exactly n minus 1 roots. And note that degree g is n minus 1. Then by problem 22a, which we just did, there's a polynomial f of x with f prime of x equal g of x. Furthermore, f has degree equal to degree g plus 1, which is equal to n. Right, similar type of thing for the other parts of this problem. They want f prime of x to equal 0 for no x if n is odd. So let n be odd, then n minus 1 is even, and let aj, j going from 1 to n minus 1 over 2, which we know n minus 1 over 2 is a integer, a positive integer, because n minus 1 is even, right? Let that be a set of positive real numbers, then define g of x to be the product, j going from 1 to n minus 1 over 2 of x squared plus aj is a polynomial of degree n minus 1 with no real roots. Then again by 22a we get we know that there exists a polynomial that differentiates to give us that. All right, part C, f prime of x equals 0 for exactly one x. For n even, all right, let n even, then f of x equals x to the n has the required property since f prime of x equals n x to the n minus 1 equals 0 if and only if x equals 0 for n equals 2k, meaning n is an even integer or an even natural number greater than or equal to 2. All right, and then part D, f prime of x equals 0 for exactly k numbers x if n minus k is odd, right? Let aj again be a sequence of distinct positive real numbers, j going from 1 to n minus 1, and let n minus k be odd, that n minus k minus 1 is even, and we can define g of x to be the product of x minus ai, I going from 1 to k, times the product of x squared plus aj, where j goes from k plus 1 to n minus k minus 1 over 2. Then g has degree n minus 1 and has exactly k roots. Then by 22a, there's a polynomial f of x of degree n, such that f prime equals g of x. Okay, question 24, part A. The number A is called a double root of the polynomial function f if f of x equals x minus a squared times g of x for some polynomial function g. Prove that A is a double root of f if and only if A is a root of both f and f prime. All right, here's my proof. Part 1, let A be a double root of the polynomial function f, then f of x equals x minus a squared times g of x, or some polynomial g of x. Clearly, A is a root of f. Then consider f prime. F prime by the product rule is 2 times x minus a times g of x, plus x minus a squared times g prime of x, which if you factor out the x minus a, gives you x minus a times 2 times g of x, plus x minus a times g prime of x. F prime is a polynomial and a is a root. All right. Then going in the other direction, let a be a root of the polynomials f of x and f prime of x. Then f of x equals x minus a times g of x for some polynomial g of x. Also, f prime of x is g of x plus x minus a times g prime of x, again by the product rule. Excuse me, is a polynomial. Since a is a root of f prime, and x minus a is a factor, then x minus a is a factor of f prime. So f prime of x equals x minus a times g of x over x minus a plus g prime of x. That implies that g of x over x minus a is a polynomial because a is a root of g of x. Then f of x equals x minus a times g of x equals x minus a squared times h of x, where g of x is x minus a times h of x for some polynomial h of x. Therefore, a is a double root. Right, and then question 25 is related to that. If f is differentiable at a, let d of x equal f of x minus f prime of a times x minus a minus f of a. Then we want to find d prime of a. In connection with problem 24, this gives another solution for problem 920, which is one of the exercises that I did in the video for the exercise set for chapter 9. So if you want to see that, you could take a look there. But here's the solution. It's very, very straightforward. Just take the derivative of d. You get f prime of x minus f of a, and then evaluate it at a, and obviously you get 0. Okay. Question number 26. This problem is a companion to problem 3.6. 3.6 is a problem that I have done way back when I did the exercise set for chapter 3. So if you want to see that, you can take a look at that video. It's the problem on Lagrange interpolation. Right? Let A1 through AN and B1 through BN be given numbers. Part A, if x1 through xn are distinct numbers, prove that there's a polynomial function f of degree 2n minus 1, such that f of xj equals f prime of xj equals 0 for j not I, and f of xi equals ai, and f prime of xi equals bi. He gives a hint, remember problem 24. All right. You also have he also gives you the hint of like question 3.6, the Lagrange interpolation. So here I'll define fi of x to be this polynomial function here. Alpha I x plus beta I times in parentheses the product x minus xj over xi minus xj for j going from 1 to n, j not I all squared. All right. If you take the derivative using the product rule and the chain rule, you end up with this complicated looking function here. It's just a polynomial though, right? If we choose alpha I and beta I conveniently, such that fi uh, evaluated at xi is alpha I xi plus beta I equals ai, then we can find out what the coefficients alpha I and beta I have to be, which is what I do down here. The derivative of fi at xi is alpha I plus ai times 2n minus 4, and I'm going to set that equal to bi. Let me just show you where this comes from here, because it might not be obvious. If you evaluate this at xi, this part here goes to 1, so you get alpha I times 1. This part becomes ai. 2 obviously stays 2. This is 1, so you get 1 times 1. And then this is n minus 2. And when you simplify that, you get the expression that I have over here, right? And I'm setting that equal to bi. Then we can solve for ai. That's equal to bi minus 2 times 2 times n minus 4 times ai. And then we can we can plug that back in for alpha I and then solve for beta I. So you get, when you do that, you end up with beta I equals ai minus bi minus 2n minus 4 times ai times xi. All right, then fi has degree 2n minus 1, and all the conditions are satisfied. Okay. All right, and then in part B, prove that there's a polynomial degree 2n minus 1 with f of xi equal ai and I guess should this I be here? Sorry, I just realized this should be an I over here. Okay, fi of xi equals ai and fi prime of xi equals bi for all I. So you just take the sum of those functions that we defined in part A. All right, question 27. Suppose that a and b are two consecutive roots of a polynomial function f, but that a and b are not double roots, so that we can write f of x equal x minus a times x minus b times g of x, where g of a is not 0 and g of b is not 0. Uh, and then we have a bunch of parts. This was an interesting problem. I enjoyed this one. Prove that g of a and g of b have the same sign. Spivak says, remember that a and b are consecutive roots. So here's my proof. Let b greater than a be consecutive roots of f. Then f of c is not 0 for any c between a and b. In particular, g of c is not 0 for any c between a and b. Since g is a polynomial, it is continuous on the closed interval from a to b, so g of c is greater than 0 for all c in the closed interval from a to b, or g of c is less than 0 for all c in the closed interval from a to b. If not, for example, say g of c1 is less than 0, g of c2 greater than 0, then g of c3 would be 0 for some c3 between, for a less than or equal c1 less than c3 less than c2 less than or equal to b by the intermediate value theorem, which contradicts that f of c3 is not 0. All right, and then part B, prove that there is some number x with x between a and b and f prime of x equals 0. Spivak says to draw a picture. I didn't draw the picture, but he also gives a hint here. Compare the sign of f prime of a and f prime of b. Right? Here's the proof. F prime of x is equal to this expression here by the product rule. And then f prime of a, if you evaluate this at a, you end up with a minus b times g of a, which is minus b minus a times g of a, if you factor out a minus sign from a minus b. And f prime of b is b minus a times g of b. Therefore, f prime of a and f prime of b have opposite signs, since g of a and g of b have the same sign. Since f prime is a polynomial, it is continuous on the closed interval from a to b, so there's a c in the open interval from a to b such that f prime of c is 0 by the intermediate value theorem. Okay, part C, now prove the same fact, even if A and B are multiple roots. And again, Spivak gives a hint here. If f of x is x minus a to the m times x minus b to the n times g of x, where g of a is not 0, g of b is not 0, consider the polynomial function h of x equals f prime of x over x minus a to the m minus 1 times x minus b to the n minus 1. So that's what we'll do. All right, let f and h be defined as above. Then by the product rule, f prime equals that that polynomial expression there, and h of x is equal to m times x minus b times g of x plus n times x minus a times g of x plus x minus a times x minus b times g prime of x, by the way we defined h. Then g of a and g of b have the same sign for a similar reason to part A, and h of a is m times a minus b times g of a, or in other words, that's equal to negative m times b minus a times g of a, and h of b is n times b minus a times g of b. All right, so h of a and h of b have opposite signs since m, n are positive, right? They're powers of polynomial. Then since h is a polynomial, the IVT tells us that there's a c in the interval from a to b such that h of c is 0, which implies 0 equals c minus a to the n minus 1 times c minus b to the n minus 1 times h of c, which is f prime of c, and that proves the theorem. Spivak does have a little blurb here talking about the history of this problem, which maybe I'll read it to you guys just because it's kind of interesting. If I can go back to this in the book, let me see. I should have gotten my glasses out. Let me see if I can make it through with my with the lighting in this room. This theorem was proved by the French mathematician Rolle in connection with the problem of approximating roots of polynomials, but the result was not originally stated in terms of derivatives. In fact, Rolle was one of the mathematicians who never accepted the new notion of calculus. This was not such a pigeon-headed attitude in view of the fact that for 100 years, no one could define limits in terms that did not verge on the mystic. But on the whole, history has been particularly kind to Rolle. His name has become attached to a much more general result to appear in the next chapter, which forms the basis for the most important theoretical results of calculus. So just a little bit of interesting history for you there. Um, okay, now moving on to question 28. Right, suppose that f of x equals x times g of x for some function g, which is continuous at 0. Prove that if f is differentiable at 0 and find f prime of 0 in terms of g. Right, so here's the proof. Limit as x goes to 0 of x over x times g of x is equal to limit x goes to 0 of g of x, right? The x is canceled for all x not 0, equals g of 0, which is equal to f prime of 0. All right, question 29. Suppose f is differentiable at 0 and that f of 0 is 0. Prove that f of x equals x times g of x for some function g, which is continuous at 0. There's a hint here. What happens if you try to write g of x equal f of x over x? So I use the hint. F of x, oops, where would this go up? Okay. So f of x is x times f of x over x, obviously, right? Again, because for x not 0, the x is always cancel. So we'll define that as x times g tilde of x, where g tilde is f of x over x. Right? Clearly, f of x equals x times g tilde of x for x not 0. We need only show that, sorry, there should be a tilde here. We need only show that g tilde is continuous at 0, or actually, let's say, actually, we don't need a tilde here. We need to you'll see as we go as we go through the proof. Actually, we want a function g that will be using g tilde to define, but it's not the function g that we want is not actually g tilde. All right, so f prime of 0 exists since f is differentiable at 0. Then f prime of 0 equals the limit as x goes to 0 of f of x minus f of 0 over x minus 0, which is the limit as x goes to 0 of f of x over x, which is equal to limit g tilde as x goes to 0. Lastly, we can define the function g of x to be equal to g tilde at x if x is not 0, and f prime of 0 when x is 0. And then you get what you want. So f of x is x times g of x for all x, and g is continuous at 0. Okay, question 30. If f of x is x to the minus n for n in the natural numbers, prove that the kth derivative of f evaluated at x is negative 1 to the k times n plus k minus 1 factorial over n minus 1 factorial times x to the minus n minus k. That's actually equal to, just to write it in a more convenient way, that's equal to negative 1 to the k factorial times n plus k minus 1, choose k, times x to the n minus k for x not 0. And the proof is just an induction proof. So induct on k. Um, the first derivative is just a power rule, so we don't really need to belabor that. go to the inductive step, assume the formula holds for some k and n with k between 1 and n, then consider the k plus first derivative, right? Then that's equal to this by the inductive hypothesis, and then we can apply, sorry, just bear with me for a second. Then we can apply the derivative here, which gives us this expression over here. And then we could just do some algebraic manipulation to get what we want. So multiply by k plus 1 over k plus 1. And notice that n plus k times n plus k minus 1 factorial is n plus k factorial. So, and k factorial times k plus 1 is k plus 1 factorial. Then notice that we end up, whoops, notice that we end up with this expression here, which is exactly what we want. Right? And that proves the theorem. Right, and then I think this is 31 is the last problem that I did in this exercise set. So 31 says prove that it is impossible to write x equal f of x times g of x, where f and g are differentiable, and f of 0 equals g of 0 equals 0. Spivak gives a hint. He says differentiate. All right, so let x equal f of x, g of x, and fg differentiable, and assume that f of 0 equals g of 0 equals 0. Then 1 equals, by the product rule, f prime of x times g of x plus f of x times g prime of x for all x. In particular, if you evaluate at 0, you get 1 equals f prime of 0 times g of 0 plus f of 0 times g of 0, which is equal to 0 by the way we defined f and g at 0. And this is a contradiction because 1 is not 0, right? Therefore, no such functions exist. Okay, and that's the exercises for chapter 10. Okay, I got a bunch of videos coming out soon. I just have to have time to record them. I know it's been a while since I posted a video because I was having some problems with my internet. But now that's back up and running, and I should be able to start posting videos again. So be on the lookout for a slew of videos that should be coming out pretty soon. I won't be able to post any more videos today because I'm actually appearing on a podcast later on in the day. So I'll be doing that for the rest of the afternoon. But anyway, keep an eye out for that stuff, and I'll see you guys in the next video.